We trust medical devices with our lives, right? But have you ever really stopped to think about what's actually inside the machines that monitor us, diagnose us, and sometimes even keep us going? Well, today, we're going to go microscopic to uncover the hidden electronics that are the true heart of modern medicine. You see the polished, clean exterior of an MRI machine or heart monitor, but the real magic, the actual intelligence powering the whole thing, is happening on a scale you can't even see. So yeah, it's about time we popped the hood and took a look inside. So here's our game plan. We'll start with what these tiny engines are. Then we'll dive into the incredible challenges they face, the specialized solutions for different medical needs, how they're actually made, and finally, the huge impact they have on all of our lives. Alright, so first up, what is this hidden component that's basically the brains of the entire operation? We're talking about the printed circuit board, or as you probably know it, the PCB. And that analogy is perfect. Just like our own nervous system carries all those critical signals that control our every move, the PCB is what routes power and information to every single part of a medical device. Now, in a machine that is keeping someone alive, a single misfired signal isn't just a glitch, it can literally be the difference between life and death. So perfection isn't just a goal, it is the absolute minimum requirement. But creating a flawless nervous system for a life-sustaining machine is, as you can imagine, incredibly difficult. These circuits face a unique and intense set of challenges that you just won't find in something like the smartphone in your pocket. Okay, so this table breaks down the three biggest hurdles. First up, compliance. We are talking about the strictest government regulations possible, often called Class 3, which is reserved for life-sustaining devices like pacemakers. Every single component has to be meticulously tracked. Second, you've got form factor. Medical tech keeps getting smaller. Think wearable sensors or tiny implants. The circuits inside have to shrink right along with them, all while packing immense power into a microscopic space. And finally, reliability. These boards have to work flawlessly in some really extreme conditions. We're talking intense heat, harsh sterilization chemicals, and even the shock of being dropped. Failure is just not an option. So, how in the world do engineers solve these massive problems? Well, there's no single one-size-fits-all answer. Instead, they've developed a whole portfolio of specialized PCBs, with each one designed for a very specific medical job. For instance, take a look at flexible polyamide PCBs. The material they're made from can literally bend and wrap around things without breaking. This makes it the perfect choice for technology that needs to conform to the human body, like the complex circuitry you'd find in modern prosthetics or even in medical implants. But what about all that high-power equipment? Things like surgical lighting and big medical scanners generate a ton of heat, and that's exactly where metal-clad PCBs come in. They are designed specifically for fantastic heat management, which keeps these powerful tools running safely and effectively right in the middle of the operating room. Remember that form factor challenge we talked about? Well, this is the solution. HDI, or high-density interconnect circuits, are just marvels of miniaturization. They pack way more conductive pathways into a much smaller area, so you get incredible performance in a tiny, tiny footprint. This is the tech that makes things like advanced, almost invisible hearing aids a reality. And for the absolute toughest environments out there, you've got ceramic PCBs. Think of these as the tanks of the circuit world. They've got fantastic thermal conductivity and are super resistant to chemicals, which lets them operate in extreme temperatures where other boards would just fail completely. And finally, you can get the best of both worlds with rigid flex PCBs. Just imagine a medical device that has a solid, rigid screen, but it also needs to connect to a flexible, wearable sensor. This hybrid technology seamlessly links the two different parts, giving you both the stability of a rigid board and the versatility of a flexible one. So we've seen all the different kinds of boards, but how do they actually go from being an idea to becoming a finished, life-saving component? Well, the journey itself is just as precise and demanding as the technology. Everything starts with prototyping, where all the concepts are tested and perfected. Then comes really deep engineering support, where experts help choose the exact right materials and make sure the design can be manufactured effectively. After that, the fabrication begins in these highly advanced facilities. But it doesn't end there. Crucially, there's lifecycle support, which means that even after a product is being used in a hospital, it's still being monitored and supported. So when you combine these extreme demands, these innovative solutions, and this meticulous creation process, the result is a technology that underpins nearly every single part of modern healthcare. And their impact is truly everywhere. I mean, think about it. That massive MRI machine scanning for tumors, powered by PCBs. The tiny glucose monitor that a person with diabetes carries in their pocket, also a PCB. The cochlear implant that allows someone to hear for the first time, or the infusion pump delivering life-saving medication with perfect precision, you guessed it. These tiny circuits are the unsung heroes working silently inside it all. This quote really gets to the heart of the whole thing. It's not just about manufacturing a component, it's about an unwavering commitment to precision. And that phrase, customer delight, in this context, doesn't mean a happy purchase. It means a device that works flawlessly, giving a patient and their doctor complete confidence when it matters most. So, the key takeaway here is this. The trust we place in our medical technology, that belief that it will work when we need it most, is built entirely on the flawless performance of these tiny, sophisticated, and absolutely critical circuits. It really makes you wonder, doesn't it? As these boards get even smaller, more powerful, and more integrated with the human body, what's next? What new possibilities in healing and diagnostics are just waiting to be unlocked by them?